Hello and welcome to Saturday's edition of Cracking the Cryptic, where today I am going to, with some trepidation, attempt the puzzle you've all been requesting for the last few days. This is Phistomefel's latest offering, and it has absolutely melted through our testers. None of them have even been able to place a digit in this one. And that makes it daunting to say the least. In fact, Phistomefel himself emailed me to say that it would be a gamble to attempt this in a live solve. He thinks it's extremely difficult, but touchingly, he remarked that if I did spot the break-in, I would like it. So that's the challenge today. Now, this has been on Logic Masters Germany for a few days, and some people have managed to solve it, including, of course, CWG2000. Now, I don't know who CWG2000 is, but I do know that they are an incredibly good Sudoku solver because they solve basically every puzzle that appears on Logic Masters Germany. Literally every puzzle. Now, CWG2000 wrote a comment under this, having solved it, to say, and they used the word question instead of puzzle, but they said this is the most beautiful question they have ever solved. Now, that is praise indeed from somebody as prolific as CWG2000. So I think this puzzle is probably a masterpiece. I just hope I get to experience some of the wonder. So wish me luck. What else do I want to mention? Well, quick mention, those of you who follow us on Twitter will already be aware of this because I tweeted about it yesterday, but I will actually be appearing in an upcoming audio sitcom called The Night Crew. I'm not sure when it's being released. It's pretty soon. It's the work of Peter C. Hayward, who is obviously also a brilliant puzzle constructor and was helping us with our book. He asked me to play a part in this. In fact, he's even done some graphics. Let me find the graphics. Where's the graphics? Here we go. It's a cartoon me. Well, some people said it was a cartoon me-con, which is a bit harsh. I mean, I may look, a little bit like the enemy in Dan Dare, but not a lot like it. Anyway, that's not the part I'm playing. It's not a me-con. But yeah, I'll put a link under this video, and if any of you might like to listen to that, I would recommend it. Not for me, I hasten to add, but there's a lot of very talented people in and behind the show. Now, over on Patreon, of course, we've got our Wonders of the World Sudoku hunt. We're still getting correct entries, which is marvellous. If you are a patron and you haven't attempted that hunt yet, you must do that. It is absolutely, it's great content and it's a lot of fun. And so I highly recommend it. And of course, tomorrow we're planning to release Scott Strosal's video where he shows you how to solve his Sudoku challenge, tracking the triptych. So that's definitely worth watching as well. Other than that, it just remains for me to wish Xavier a happy birthday and get on with the rules of this puzzle. We've got normal Sudoku rules apply. The digits on an arrow add up to the digit in the corresponding circle. So that's completely normal arrow clues. A clue outside the grid indicates the sum of the digits on the corresponding diagonal. On this diagonal, digits may repeat if the other rules allow it. So completely standard little killer rules as well. So let's, if you're not familiar with those, that means those two squares, they're obviously emanating from this circle here. Whatever those two squares add up to, you've got to put it in the circle. And then on the diagonals, basically this diagonal here has to sum up to 29, and you can repeat digits on the diagonal, but not frivolously. So you can't do that, for instance. That most certainly breaks the rules of Sudoku. Don't do that. You won't get the answer right. Now, do have a go at this. The way to play is to click the link under the video. I suspect this is monstrously hard. Let's get cracking. Now, so what can I see immediately? The first thing I can see is useless little killer clues, which is no surprise. I mean, if our testers, as I say, our testers can't place the digit in this puzzle, so there is not going to be anything straightforward here. And if we look at the little killers, 3 cells with a total of 15, we're averaging 5, which is exactly what you don't want to average because it's completely the average. Same thing here, 6 cells adding to 30, that's averaging 5 as well. 2 cells adding to 10, that's averaging 5. 4 cells adding to 21, well, it's averaging very nearly 5. That one's 7 cells. Okay, that one's averaging just a shade over 4, so that's nearly useless. 13, just a shade under 5, and just a shade under 5 again. So these little killer clues are actually, I would go as far as to say, strangely average. I'm almost wondering if that's where we need to focus for the break-in, because they're so average. Let us do the other thing we tend to do with complicated puzzles, which is, let's just highlight all of the little killer clues and take a quick stare at that. I missed off that one. There we go. Now, does that pattern remind you of anything? It doesn't remind me of anything. There's no... they should make this into a scientific study. If you can see, like, you know, the answers to the life, the universe and everything hidden in these yellow squares, then it certainly says something about you, but it doesn't say anything about me. I've not got a clue what that is. Okay, right, so I think it must be the arrows that we have to look to. And I've been doing quite a lot of arrows recently because of our upcoming Arrows app. So, well, the first thing I'm seeing is, look, we've got spectacles everywhere. It's like Phistomefel is deliberately haunting me. He's got spectacles in every one of these corner boxes. Okay, so, I mean, I can see these cells, for example, are all in the same row of the Sudoku, so they've got to be different. So the minimum value of these squares is 10, 1 plus 2 plus 3 plus 4. The minimum value of those squares is 6 with 1 plus 2 plus 3, which means that the minimum value of these squares is 16. Yes, that is complete and utter bobbins. That is no use to man or beast. I was never expecting those to add up to less than 16, let me tell you. Something very similar down here. In fact, it's identical, isn't it? We've got 16 there as well, so that's no use. Column 9, look, that does have a lot of arrow real estate in it. So, that actually, this is interesting. The problem is I can't get too excited about this. This is really sad because I know the testers haven't been able to do anything. I'm at a slight advantage. I don't think this will be the break-in, but it is interesting, so I should talk about it, because these squares, the minimum I can include in 6 cells in the same column of a Sudoku is 21. If I make these 6 squares 1, 2, 3, 4, 5 and 6, that will add to 21. So these squares have a minimum value of 21 and a maximum value of 24, because they could be 7, 8 and 9. Now, that doesn't even mean we need to have a 9 in one of these, because unfortunately 6, 7 and 8 add up to 21. So, but as they must add up to at least 21, you can't put low digits in there. You couldn't have 1, 2 or 3 in these circles, because that will mean you'll have to either repeat a digit in a circle or use a double digit number, which is probably not a good idea. So if these are 21, these would be 24. And if these are 24, these will be, yeah, okay, there's something strange going on. The cells in the gaps in column 9 combined with the circles in column 8 are like the complement of each other. They add up to 45. So these yellow squares add to 45. And by the way, if any of you are wondering how I know that, that's because I know a secret. If you add up all of the digits from 1 to 9, and obviously column 9, for example, will include all of the digits from 1 to 9, you get 45. So I was eliding a bit over some of the logic there, but that's how I know that. So if these squares add up to 22, for example, so 22 would be the sum of the yellow squares, I know those 3 squares would have to add up to 23. So these squares together add up to 45. And that is... I mean, I can do something with this 10 arrow actually. Let's just have a quick look at that. The 10 arrow, how do we make 10 in 2 cells? Such that it meets the conditions that this square has got to be lower than this square, because this square is the circle and it's the sum of those 2 squares. The various ways are 9, 1, 8, 2, 7, 3 and 6, 4. So this has to be one of the higher digits. Oopsie. This has to be one of the lower digits, and therefore we will know the possible values of this square. If this is 9, 1, this will be 8. If this is 8, 2, this will be 6. If this is 7, 3, this will be 4. You always get an even digit there. That's weird. So maybe this is parity that we need to use. Parity is interesting in arrows because there is a feature of arrows. If you add up any arrow and its circle, that will always equal an even digit, because obviously even if this domino here adds up to an odd number, once you add the odd number to an odd number, you get an even number. So I'm just wondering, I mean, those must add to an even number. This is an even number. Therefore, we know that those 4 squares must add to an odd number. Yes, you're right. That's useless. Sorry. Right. Maybe I can do something. If this is 8, then these squares have a minimum value which is higher than 21. The minimum value would be 15 plus 8, which is 23. And this would be a 9. So you'd have to have an 8 in one of those squares. You'd have 9 here. You'd have to have an 8 down here. But this could be 23 or 24. So you'd have something like this going on. And I don't like doing this actually, because this just feels like bifurcation. I'm sort of guessing that this is an 8 and then seeing what it does. Sorry, no, I don't want to do that. I don't feel that that's elegant at all. Right, so what on earth am I meant to do here? What on earth am I meant to do? I've got... Maybe I could combine these arrows maybe. That would give me 31 into the yellow cells, which means that there's a tiny relationship between, let's colour these in, between these 2 squares and those 4 squares, because I know the box will contain the digits 1 to 9 and add to 45. So what could that could be double 1, I suppose, in theory. If that's double 1, then we know those squares add to 29, so we know those squares add to 16 to make 45 altogether. And as we increase these, yeah, we need to increase these as well. So as we move up from double 1, these get 17, 18, 19, 20, which is absolutely useless. Oh, bother. I'm not surprised, I have to say. I was fearing that this was going to be the case. Now, what else have you hidden in here, Phistomefel? Is it geometry? Can we do some geometry on the grid? Try and get maybe row 1, row 9, column 1, column 9. So let me just explain what I mean here. What I can get is a relationship. In fact, I'll show you the relationship, then I'll show you how to prove the relationship. Those squares there come out. So these purples are equal to the greens. And when I say equal, I don't just mean they add up to the same number. They are the precise same set of digits. And that actually might be interesting because there's 8 circles there that have to fit into the greens. Let me just show you why this is true. Fill these in. So if I was to ask you what the purple squares contained, we could very confidently say it was 2 sets of the digits 1 to 9, because this row obviously is a complete set of the digits 1 to 9, so is this one. Now if I wanted to remove from those 2 sets of the digits 1 to 9 those 2 squares, so let's imagine that I want to remove these 2 squares. Now those 2 squares are obviously different digits, so I'm just going to remove them from one of the sets of the 1 to 9. So we've got 2 complete sets of the digits 1 to 9. I'm going to remove these 2 squares from one of those sets. What will be left in that set of the digits 1 to 9 if I remove these 2 squares from it? Well, clearly it's going to be whatever's in the rest of this column, because this altogether represents a complete set of the digits 1 to 9, so if I remove those 2 squares from it, I'm just going to be left with those. So now we can come across here and do exactly the same thing on this column. So if I want from the other set of the digits 1 to 9 in the purples, which is still complete, remember, because I've only meddled about with one of the sets so far, I'm going to remove those 2 squares from the purples. And in that set, therefore, I will be left with those exact cells. So the purples and the greens are exactly equivalent. And I just want to stare at this for a minute, because I've got a lot of, well, it's a slight, actually I'm slightly over-egging the pudding here, because there are 2 single cell arrows actually, aren't they? So this square could actually be a 1. So I was about to say that circles on average have to be relatively high digits because they are the sum of other digits, which is not true for that one or this one. But the others it's true for. It's true for those. Those all have to be relatively high digits. And in the green regions, a lot of the digits are on arrows. So in theory should be lower than... There's something going on here, isn't there? Arrow cells on average should be lower than the circles, and yet we know that there must be, we know these add up to at least 21. So you can't, so if these add up to at least 21, the minimum these add up to is 21. So the lowest digit you can include in a yellow is a 4. So there must be 1, 2 and 3 in the greens, which means I've got to put 1, 2 and 3 somewhere in these purples. Now in this column, well, you can't hide the 1, 2 and the 3 in column 1 in the corners. You can't like make this a 1, 2 pair, because then this arrow and this arrow would have a minimum sum of 3 plus 4 and 4 plus 5, which is 18, which would require double 9, which won't work. So there must be a 1 and a 2 on these arrows, or perhaps both, which means the purples have to include a 1, 2 and a 3 from this side, and at least a 1 or a 2 from this side as well. which the problem is these are possible, aren't they? That's the problem, is you can hide digits in these squares and they can be low. They can just be low digits. The other thing you could do, actually, is I could just delete cells from the greens and the purples, because this purple is equal to those greens. So okay. So at the moment we've got a situation where the greens and the purples contain the identical set of digits, so they add up to the same number. Now, I'd have to disregard the identical sets of digits if I start deleting stuff, but that cell and those two cells add up to the same number, so we can just delete them from both sets. Now we know that the purples at this point still add up to the greens. So, this could be interesting. Same thing here. Same thing in all of these corners. The purple takes care of two greens. These are the same sum. So I'm going to delete them. Delete them. So now what have I got? Now I've got the 6 greens have to add up to the same number as the 10 purples. But I know less about the greens than I used to, because I'm not really covering the arrows. We can increase the number from 10 though, because I could replace that one with those two. This is actually really interesting. If I get rid of that square, obviously these two add up to the same number as that circle, so I could do that. In fact, I could force them all into box 2 and box 8. Is that... That will allow me to relate them to 45. Can't quite see whether this is doing anything, but I'm tempted to try and shunt all of the purples into box 2, which I can do simply by mirroring that one in there. And I can do it down here, because that's got to be the same as that. That's got to be the same as this. So now we've got a situation where the 6 greens are equal to the 12 purples. So on average, a green has to be double the value of a purple. Now this is getting very constrained. So the minimum I could make the purples now would be 21 again. It's the same as over here. If I put 1, 2, 3, 4, 5 and 6 into those purples, did the same at the bottom, I'd get 21. 21 is 42. 42. Now, I've got it. Yeah, I have got it. I understand how to start the puzzle. And in fact, I'm going to get a digit there, because those squares, what's the maximum I make these squares? 7, 8 and 9. Now look here, what's the maximum I can make these squares? I could put a 9 here, no problem. But this domino, it's got to add up to a single digit number. So the maximum this domino can be is 9. And in fact it will be 9. I'm going to get this digit as well. Let me show you why. If this adds up to 9, 9 plus 9, 18, plus 24 is 42. So the maximum you can possibly make the greens is 42. And the minimum you can possibly make the purples is 42. So if you make the purples just one higher, you can never make the greens add up to enough. And you can't make the purples lower. So everything, in fact, the answer to life, the universe and everything is 42, which I'm almost wondering whether Phistomefel has done that deliberately. He's so brilliant, he probably did. I can well imagine he's a Douglas Adams fan. That is absolutely, I mean, it's incredible. Absolutely incredible. So now we know these digits are 1, 2, 3, 4, 5 and 6. We know these digits are 1, 2, 3, 4, 5 and 6. We know these squares, therefore, are all 7, 8s and 9s. We're going to get some of these. I can see I can immediately put 9s into these regions because of this 9. That's got to be a 9. And then that's got to be a 9 by Sudoku. Now 9 has to be down there. 9 has to be in one of those two. 9 can't be in this one because this is a short stubby arrow. So if that's a 9, this has to be a 9 as well, and this can't be a 9. So that's not 9. This must be 9. 9's in one of those two. I don't think that one is a short stubby one. It's a little bit hard to see. I think that's a 2-cell arrow. Oh, but this is a little stubby arrow as well. Yeah, this is a 1-cell arrow, so this can't be 9 because that would put a 9 in here. So that's not 9, this is 9, which means this is 9. And suddenly the puzzle is revealing its secrets. Now this square is not 9 anymore, so this square can't be 8 anymore. And that probably means that one can't be 1. No, it can't, because that would require a 9 because of the 10 arrow. 1, 2, 3. I've got 7 9s in the grid. 9 is in one of those two squares. 9 is not there. So 9 is in one of these two squares. And right, let's just sit back and think, because suddenly we have a bit of progress. Like 15, there's a 15 diagram. I've not used, I don't think. Have I used the little killer clues at all? I don't think I will. I've pencil marked that one a bit. But I don't think I've really used them. So those have to add up to 6. They're either 1, 5 or 2, 4. Okay. 21 has already got 18 on it. So these two squares have to add up to 3, so they can be very much restricted. They've got to be 1 and 2, and they are different, so we might even have to colour them. In fact, I'm quite tempted to immediately... Is that worth colouring? Actually, it's probably not worth colouring, because I haven't actually got any other cells in the grid that can just be 1s and 2s. But we've got to try and remember these are different. Um, 29, we've got... no, nothing. 30? No. 13. Oh, look, we've got... Okay, look, we've got the short stubby arrows. Let's do some stuff with those. They look like they can both be 1, 2, 3, 4, 5 and 6. Okay, that's not a particularly good restriction. 7, 8. Where does 7 and 8 go in box 7? This 7, 8 and the 7, 8's here. There's a 7, 8 pair. So that means 7 and 8 have got to be in those squares in box 9. Don't think... Looks like with all of the options along this arrow that this could easily be 7 or 8. 7, 8. There's now a 7 or an 8 on the 13 diagonal. So this can't be a 6, because if it's a 6, we're already going to break the bank. So this can't be a 6 either. So the maximum value of this square is 5. Oh, but hang on, I haven't used this arrow either. This domino, yeah, hang on, this domino adds up to 9, and it can't use 8, 1 or 2, 7. So this is 3, 6 or 4, 5. So the minimum value of those two squares together is now 10. So this can't even be 3. If this is 3, the best you'll do with this square is 4, and 3 plus 4 plus 7 is 14. It's not 13. So this square is 1 or 2. That means this square is 1 or 2. Now, does that matter? So now, can that really be? That can't be 6. That's exactly the same reason this can't be 6. So if this can't be 6, this can't be 3. So this... oh no, this could be 3. If that's 8 and that's 2. So we can almost get some stuff here. The 18 diagonal. Oh yeah, okay. The 18 diagonal as well. Look, this square is restricted because the minimum value of those two squares is 14. So this definitely can't be, it can't even be 4. That's got to be 1, 2 or 3. 14. So the maximum value of this square is 3. So this is very restricted as well. Just wondering whether it's worth trying to put these together in the same sum, because then I would know the sum of these two. So if I look at this as a sort of, you know, two diagonals, these has to add up to 31. I've got 15 there, so these squares have to add up to 16. Can we do anything with that? So if this was a minimum, these would have to add up to a maximum of 9. I'm not sure. I'm not sure whether that's okay or not. It might be. I can't see why that's a problem. Apologies if everyone's shouting at their screens now. It does feel like this is quite restricted. Can this be 9? If that's 9, if I've got, what have I got here? 15. I need 16 into these. If this is 9, these have to add up to 7. That could be done, couldn't it? If this was a 1-2 pair and this was 3 and 1, that would add up to 7. So that's not proving useful. I don't think I can restrict this at the moment. Right, let's look somewhere else. We can look for... where? Where do we look for something else? We could... this... no, that can be 4 different things. 1, 8, 2, 7, 3, 6, 4, 5. Do we know what this is? I don't think so. Wow, 7 and 8 is a bit restricted in row 1. 7 and 8 have to be in 2 of those 3 squares. But that looks completely fine. I don't know what to do. Okay, where else do we look here? We've got to look at... oh, I know what I can look at. I know what I can look at. I looked at this column and this column's gaps. These had to add up to 45 from the work we did earlier. I now know 2 of them. So these add up to 18. That means these squares, let me get this right, that one and that one, have to add up to 27. Yeah, okay. That also doesn't seem to be helpful. What about if that was 7 and 8? If that was 7 and 8, these would have to add up to 12. Is that possible? It looks more than possible. Looks possibly even probable. Ah! What on earth do you do next? I thought the break-in was going to be hard, but it doesn't get any easier. I can't believe it's these 20. This 29 diagonal's got too much optionality about it. Can I do more with these ones then? 13 again. 13. Can that be 5? Yeah, it can. 5, 7, 1. That's absolutely fine. 18. So, still. Is there something about 3? Is 3 here a problem for some reason? That would require these to add up to 15, so it would require double 7 and 1. Is double 7 and 1 impossible? Not seeing why. Let's try them together again. We've got 31 now. These have to add up. These have to add up to 16 because we know they add up to 15. Right. I can eliminate a 3 from this square. Because if that's a 3, this has to be at least a 4. 7 plus 7 is 14. And these two would have to add up to 2, which is impossible. You can't double 1 them. So this square is not 3. That gives us a 1-2 pair here. So I could... yeah, I am going to colour this now, because these two are the same. So cells like this can't be a 1 or a 2 anymore. Because they see this square, which is a different colour from this square. So let's have a look at this. We can use red and blue. So you can see this square sees this red and it sees this blue. So it sees 1 and 2 between the two of those. So this square has become a bit more restricted. I've now got these two squares have got to be 3, 4, 5 and 6. I'm clutching at straws a bit here, I think. 1, 2, 1, oh no, hang on. 1, 2 in this column are now forced into these 3 squares. So those squares are 1 and 2. So this square can't be a 1 or a 2, and this square has to be a 1 or a 2. Is that enough? Does that do anything for us? I've got yes, I've got a 1-2 pair here now. Lovely. So this square can't be a 2. I'm not sure if that rule... Oh, that must rule one of the options out from there. Does that rule 6 out from here? 6, 4, 2. Yes, it does. That's not 6. That's not 4. So 6 has come out from here. 4 has come out from here. 1, 2 can come out from here because of the 1-2 pair. This 9 arrow now... yeah, hang on. This square is restricted as well. Because this can't be 1 or 2 anymore either, because this domino is either 3, 6 or 4, 5. Now what do we do? I don't know. There must be something else to do. We can... It's always the way with Phistomefel. His puzzles are totally baffling. They make me feel so stupid, I cannot tell you. I'm sure that there is something very obvious I'm meant to see here. Actually, I'm not sure it's very obvious, but I'm sure there's something that is more obvious than I feel I'm making it look. Okay, come on. How do we make more progress in this puzzle? We can... If I could relate... You see, I can't... I'm wondering whether I can connect the colouring of the 1s and the 2s somehow. That might be helpful. Is there a way of doing that? Or is there... See, these... Oh, these two are different, aren't they? Ah, I haven't used that. These two are different because they of the 21 clue. So this square sees both colours of the 1 and the 2. So this is not 1 or 2. This is not 1 or 2. Oh, now look at box 2 and ask where 1 and 2 go. And the answer is that we don't really know, but they definitely seem to be in those 3 squares. So there's no 1 or 2 here. This square becomes a 1 or a 2. Oh, good grief. Now look, these are on an arrow. This is 1 and 2 are on this arrow, so this is a 3. Just look at what this 3 does. Look at what it does. It removes 3 from these squares. That's the first thing it does. It removes 3 from this square. That bounces back in here. And now where does 3 go in this box? On the arrow. So this 9 arrow is now 3, 6. That removes 6 from those squares and 6 from this square. That removes 3 from this square. That means we can colour that one blue. That might be interesting down here for the stuff in the bottom left hand corner. But let's carry on up here for a second. I've now got a 4-5 pair in row 2. That 4-5 goes in here again. This is absolutely ridiculous. So this 3 locked a 3 in here, which locks a 6 in here, which then bounces back through here and gives us a 1, 2, 4, 5 quadruple in the row. Now look at row 1 and where our square 7 and 8 can go. That can't be 7 and 8 because of those squares. So 7 and 8 are a pair in the end. This square must be a 6 by SUDOKU. 6 gets removed from these squares down here. And 6 being removed means this domino has to add up to 9. It must be a 4-5 pair. So get rid of 3 from here. That means we get a 3 in the corner. That's 3 in the corner. That's 3 in the spotlight, losing its religion. That square's a 6. This square is not a 6. I think it's quite clear we're going to have to be very careful with our pencil marking here because every digit seems to matter. Oh, 1, 2 pair here, so those are not 1 and 2. In fact, that's not 1 or 2 either because of the 1, 2 pair there. Ah, well, actually it's obvious now. There must be a 3 on this arrow because if it can't be a 4-5 pair because that would make this a 9, which it can't be. So this is so this square is a 7 or an 8 now. Because there's a 3, this is either 3, 4 or 3, 5. So this square is either 7 or 8. So there's we don't yet know really what's going on down here, I don't think. 3 is in one of those cells. I've got this 4-5 pair in row 2. What have I not placed in here? I need to place 4, 5, 7 and 8. So this square is a 7 or an 8. So it's different from this one. So I think there's all sorts of colouring going on in this puzzle. Yeah, okay, this is lovely. So this is a 7-8 pair now, so this can't be a 7 or an 8. That's a 4 or a 5, which means that's a 7 or an 8. So I'm not sure, but we might have to think about colouring the 7s and the 8s now. All of those are the same. All of those are the same. Unfortunately, that doesn't tell us the colouring of those two squares or the colouring of these two squares. I'm just going to tidy up my pencil marks. How long have I had? 45 minutes. That's not. I don't think that's terrible. Okay. Now, get rid of the 1s and the 2s from there. Okay, what have I not used? I think I've used this 15 quite well. I've not used the 30. And I don't really want to use that 30. That looks impossible. Oh, I was going to have a look down here, wasn't I? I've got all of this colouring done now. So I've got the same digit repeating on the 18 diagonal. So if this is double 1, these two squares would have to add up to 16. So they could be it could be 7, 9 or double 8. If this is double 2, these have to add up to 14, and they could be double 7. That doesn't seem terribly good, does it? Let's try them together then. What have I got there? If I try them together, it depends on what blue is. So I've definitely got 15, and then if blue is 2, I've got double 2 plus 1, which is 5. So I've got 15 and 5 is 20. These two squares have got to add up to 11. So they could be 4, 7. If this is double 1 and 2, I've got 19 in these squares. These have to add up to 12. Right, oh, that is useful. There's no 9 here, ever. This domino, what that proves is that this domino either adds up to 11 or 12. And you can see it's not possible for the 9 to be involved in either of those sums. So this, that actually gives us a 9 if my pencil marks are correct. And then, we've now got the 9s, I think. We have got all the 9s. We've got a 7, 8 here. Now, do we know the colour of this one? We do. We do, don't we? Because these two squares are either taking the total along this diagonal to 2 or 4. So we know that these two must be the same because they must be adding to an even number. Now, what does that mean? Do I know? So I must know that this is green then, don't I? That's the point. That's green. I don't know what it is, but I know it's green, so this is purple. This is quite beautiful. I have to say this is quite beautiful because now. Sorry, brief pause there. These things happen on the long videos, especially at the weekends. But I was just about to reveal why this was quite beautiful, and I will get the chance to do that now. The reason is, look, if we look in this box here, we've now got opposite colours in these two dominoes and these two dominoes. But we know the sum of those two dominoes because effectively we can divide the 18 diagonal now into 2x plus 2y because there are 2 greens and 2 blues in it. So if we just take the 2 out, we know x plus y equals 9. So I know those two squares equal 9. Well, if those two squares equal 9, what do those two squares equal? 9. because they're just the complement of whatever we put in these two squares. So if these equal 9, what does this square equal? Well, it's got to equal 4 to make the 13 square work. So this is 4, this is 5, and we have more digits. That's a 4. That's not a 5. This square is never a 6, because if that's a 6, we would have to put 3 there minimum, and that would make this square a 9. Okay, so, okay, can we go further with this? I'm not sure. It doesn't actually seem to have done very much, unfortunately. 5. I really don't think it has. Bobbins. 1, 2 pair here means that square's not a 1 or a 2. We've got a 4, 5 pair in this box, so that's not 4 or 5. There's a 1, 2 pair in box 2 as well. And now it looks like we're stuck. Where am I meant to be looking? I've almost got something interesting happening in the 30 diagonal, where I've got 2 greens. So if that's 16, these would have to be 14. So these 4 squares either add up to 14 or 16, which I think looks very doable either way. Oof, okay, this square can't be a 6 because, remember, this domino here has 2 options left on it, 6, 2 or 3, 4. If you put a 6 here, you get a 3 there, and neither of those options exist on that domino anymore, because that would have to be a 4, 3 now. But this square is just about to become a 3 to add up to 9, and we have a problem. So that square on this diagonal is now 3. And that square is 6, which does absolutely nothing. It means there's a 6 in one of those 2 squares. We get a pencil mark. We don't seem to get any elimination. We get a 3 in one of those 2 squares. You are kidding me. We got a 3 on this diagonal. Does that matter? We've got... So now we've either got 14 or 16. So if we've got 14 plus 3, we'd have 17. These squares would have to add up to 13. That would mean this couldn't be a 1 because you couldn't make those add up to 12. But it could be a 2 because you could make those add up to 11, but only with a 5, 6 pair here. 5 would be there, 6 would be there. That looks doable. Oh, bobbins. Okay. So what do we do now? We could look, actually, we could have a look again at column 8 and 9, look. Because I've now got 15 in those 2 squares. Now those squares, these squares together had to add up to 45 from the work we did earlier. We've now got 15 and 18, 33. These have to add up to 12. We know there's a 7 or an 8 in one of them. Now, admittedly, this isn't a massive restriction, but I think these squares therefore have to be from the digits 4, 5, 7 and 8. That means there's definitely it's the same. We haven't actually, I've not done anything there. Sorry, that's just completely useless. There's a 6 in one of those 2 squares, which I already knew if I'd thought about it. So, okay, so what have I not looked at? The 29 diagonal. I've still got 3 cells that are pretty much unrestricted and could all, well, we could have 8, 7, 8 down there, for example. And that would almost get us to 29 before we even consider the other squares. 15 diagonal. I've got to make sure those add up to 6. 4, 6. Good grief. Alright, I can do something with this square. This square can't be a 4. And that's again to do with this domino here. If we put 4 in here, what happens? Well, because you get a 6 here and a 2 here, so remember this square will be a 2. But because of the way that these two squares have to be a... If this is 4, and maybe I'll do it longhand. If this is 4, that has to be a 5-1 pair to make this 15 work. So this is a 2. But I've just said this square is going to end up being a 2 as well, because once this is 4, the only way of making this domino add up to 7 or 8 is with a 6-2 here. And look what happens there. That is not easy, and that's probably something easier than that to see here. But unfortunately, I'm probably best, once we're reaching this length of video, not to spend too much time trying to find it. So this square is a 5. That's a 4. That means this is a 2, this is a 1 to make the 15 diagonal work. The 4 here, look, means this square's a 5, this square's a 5, this square's a 4. There's now, we've now got a 4-6 pair in this box. This 2 means this square's a 1, so this must be 2 or 3. Let's get rid of the 3 pencil marks there. So we're not doing too badly. We've got... my 21 diagonal. Do not ignore the 21 diagonal. These have to add up to 3, so this is a 2. This is a 1. The 2 does absolutely nothing. The 1 does, you've guessed it, absolutely nothing. I don't believe it. You rotten thing. Oh, the 30 diagonal now. Look, that's better than it was. I've now got 5 on it. 5 plus 14 is 19. 11. This, look at that. This 5 has made adding these two to 11 impossible. So this diagonal cannot be double 7 in the greens. It has to be double 8. So just to show you that longhand again, if this is double 7, now you can see we've got 19 on the diagonal. These would have to add to 11. 9, 2, 4, 7, 3, 8 are all ruled out. So this would have to be 5, 6, and this square here can't be either of those squares, either of those digits. So we now know green is 8. We know purple is 7. That's going to give us, that gives us a 2 here. So red is 2. And blue is 1, and that this diagonal adds up, this diagonal adds up. This diagonal now we've got 21. These have to add up to 9 without using 1, 8 or 2, 7. So this is 3, 6 or 4, 5. That square's got to be 5 or 6. This square's got to be 3 or 4. 1, 3, 4 into the balance of this column. 2, 5, 6 into the balance of this column. 5, 7, 8 into the balance of this column. And surely this stuff down here is resolved, isn't it? We've got... No. What a puzzle this is. It's ridiculous. Absolutely ridiculous. Even after the ridiculous beginning, it has remained ridiculous. I mean, just, it's beautiful and barbarically difficult. Okay. What am I missing here? What am I meant to be looking at that I've not looked at? I've looked at everything that can be done, surely. I still don't think this diagonal is in any way restricted. I've done all the other... It's got to be Sudoku of all things. That's ridiculous that I have to do Sudoku in a Sudoku puzzle. Where is the Sudoku to be done? Are there obvious weak spots in this puzzle? There don't look to be any. 7, 8 pair there. 2, 3, 5 into those squares. Look, that's not 5. This square. Maybe this arrow. Maybe this is the arrow I've got to focus on. I've got 1, 3, 4 and 6 into those squares. 1, 3, 4 and 6. This is not 1. Can we eliminate anything from this square? If this is 4, this would have to be a 1, 3 pair, which looks possible. If this is 5, a 2, 3 pair looks possible. If this is 7, a 3, 4 pair is possible. If this is 8, a 5, 3 and a 6, 2 look possible. Good grief. So we've got to find something else to do. There's going to be some trickery. We can... And I'm not exactly sure what I'm meant to be looking at here. What I'm trying to do is just... is almost good lift this in my head. Which is a big difference between, you know, bifurcation as guessing and visualization, which I think is fair enough. But I admit it's perhaps not as satisfying as some things we can do. Let me just try and spot something. 3, 5, 2, 3, 2, 3, 2, 3, 2 rules out 4 and 5 and 7. That would force 2, 6 here. 3, 2, 6. That's 8 therefore. So this becomes 4. That breaks it. Good grief. Right, okay. I have something, but it's not very pleasant. This square cannot be a 3. Now the reason it can't be a 3 is complicated, and it's to do with this arrow, this square and this square. Okay, I told you it was complicated, but if this square is 3, you can see because this is 5, you're going to get a 2 on this arrow. So let's do this longhand. 3 and 2 go into these 2 squares. Now the interesting question is what this square can be now in order to make a valid total with this arrow. So 4 is no longer possible here. 5 is not possible because we can't put 3 here anymore, given the 3 there. 7 is not possible because 5 can't go there. So this square would have to be 8. Now if this is 8 and this is therefore 6, the question is what goes into this square? Well, this square has to be a 4 because remember, these squares were adding up to 27 and we worked out this had to add up to 12. So, but once this is 4, we get a 6, 4 pair. Boom! That square is broken. And that is horribly complicated. I'm quite sure there's a better way of doing it. But that is the way I found, and I'm taking it. That's a 2. I'm taking it and it does nothing. Oh, come on. You are kidding. Is that has literally done nothing. Oh, good grief. What does it do anything in this column? Deleting a 2 from this square means this square can't be a 6 anymore, because if this is a 6, we can't make this add up to 9. Does it do anything else? 2 and 1, sorry, 3 and 1 is still possible. This can't be 5 anymore, can it? I don't think. No, it can't. So 5 comes out of there. Seven, 8, 6. Can you put a 6 on this arrow? Oh, no, you can't. Hang on, hang on. Look, this is it. This is it. Once you remove 6 from this square, where does 6 go in the column? You can't put 3, 6 in here. For exactly the same reason, we couldn't have the 6 and the 3 interfering with this domino before. 3 and 6 just utterly, massacres this domino because it removes, it forces it to add up to 6, which this can't be. So you can't put 6 in this domino. So if you can't put 6 here, look at the column. Where does 6 go? Only there. And that might help. Not much else has, but 6. Yes, 6 forces the 10 arrow, doesn't it? So that forces the 2, forces the 8, forces the 7, gives us a 3, locks something out of this square. Now this 9 arrow can't be 2, 7 or 3, 6. So it's 4, 5 or 1, 8. Now I can see that 3, look, is on this arrow. So 3 is not there. That's just in looking at column 9. So 3 is not here. And has that done anything for us? So, hang on a minute. I put a lot of digits in. 8 is not here anymore. 7 is not here anymore. Yeah, there is stuff going on, isn't there? I'm gradually whittling this away. Or whittling away at this. These two squares had to add up to 12 as well. So once I remove 7 from here, I remove 5 from here, which this already seems to have got rid of. Once I remove 8 from here, I have to remove 4 from here. 5, 8. So this is now either 5, 7 or 4, 8. I'm not sure the order of that. Come on, Simon, there must be something we can do here. So 5, actually 5 can never go in that square now. That's it, got it. If this is 5, what do I put in here to add up to a valid total? Nothing, nothing works. This is not 5, this is 3. This is 5. That means this must be an 8 arrow because this can be no less than 3. That means that square's a 5. We know this domino adds to 12, so that's a 7. That means this is a 4, a 6, and a 1. And finally, I think I might be getting somewhere. 5 is not in those squares. Okay, that ran into a cul-de-sac quickly. 1 is in those cells in rows 5 and 6. So I've not yet put a 1 in row 4. It can only go into this square. That's not on the useful diagonal. I think this 29 diagonal is going to have to come into play at some point in a minute. 8 here means we've got an 8, 1 figured out on this side. Actually, that means this square is a 1. That means this square is not 8. That still doesn't fix the 8 though. The 8 can still be in one of 2 places in the column. Good grief. Okay. These 3 squares, we know what they are. Yes, we do. 3, 6 and 7. We know that's not 7. These squares, they are 2, 4 and 5. Do we know anything about those? The answer is No, apparently. Oh no. I don't know what I'm missing here, but it seems like the world is passing me by as I try and solve this puzzle. Maybe I've got to try and get this diagonal sorted out now. What have I got on it so far? I got 15. I need 14 from those squares. Incredibly average, of course. So this square is 4, 6, or 7. I really am not sure what I'm missing here. These squares are 2, 3, 4, and 6. Eight. 8 by Sudoku, look, in this box. Is that fixed? I think it is. 8, yes, it is. 8 goes there. So this is 7, this is 8. That means this is 5. Oh, we are getting somewhere. Thank goodness for that. This is not 6. This is not 6. This is not 5. So 2, 3, 4, and 7 into this square. That can only be 4 or 7. Looking at the column. 4, 6 here. Have we got anything else? We've got... I don't know if we do. I really don't know if we do. Come on, Simon, what are you missing here? I don't know. This video is one of the longest we've ever done. I think I'm getting tired as well. I hope that you'll forgive that. It's actually getting dark here, such is the length of this video. 4, 6. So this has definitely got 2, 3 into those squares. Oh dear, come on, what are you missing? I must be... Oh, I know what it is. It's the 30 diagonal, isn't it? Once you get this 6, you know this square has to be a 3. This is a 4. And does that do it for us? It gives us more yes it does. This 3 sees a 6 here. Therefore we get a 3, 7 pair. This is not 6. 2, 4, 5 triple there. 2, 3, 4, 7 quadruple there. 2, 5 pair here, so this is not 2. This is not 4 either because of this 4. So the 3, 6, 7 triple. So now, maybe at last, this is going to be the key. 15. I need these to add up to 14. Yes. This square can't be a 7. If that's a 7, you can't make those other two squares add up to 7, because even if you put 6 here, you can't put 1 here. And this is 3. This is 7. Please, please keep going. That's a 6. That's a 4. That's a 6. That's a 7. This is a 3. There is a storm going on outside now, so clearly Phistomefel is angry that I'm about to finish his puzzle, I think. Right, now this diagonal again. Let's revisit it. I've now got 15 and 9 is 24. This square has to be a 5, and that 5 is, I think, going to finish the puzzle. Wow. Oh my goodness me. Click check. Yes, I did it. It took ages, and it was monstrously hard, but I did finish. I did finish. Wow. What a puzzle. I mean, even after the break-in, which the break-in is beautiful and very clever and unusual. But what surprised me was after that, it's just unremitting. There's some beautiful logic all over the place as well. And even when you find some lovely deductions, they don't go, it doesn't, the puzzle never collapses. It keeps sort of holding out on you. It's a remarkable setting feat. It really is. I'd love to know how many of you solved that. I'd also love to know if there was a quicker way of doing the whole back end of that puzzle. I have a horrible feeling that I missed something and there might have been a more, a swifter way. So let me know in the comments if you found a swifter way. Let me know in the comments if I deserve a clap or not. And yeah, I enjoy reading them, especially when they're kind. Thank you so much for watching, and we'll be back later with another edition of Cracking the Cryptic.